Okay, so finally you have designed that well-performing PID controller. And also the stability margins, the gain margin and the phase margin are okay. So now you're ready? Unfortunately, you're not. There's still one aspect that needs your attention, and that's the controller's sensitivity. And that is the topic of this video. So we're going to discuss three aspects. We're going to look into the sensitivity, the definition, and we are going to look to the absolute value of the sensitivity. We're going to look into the impact of a P controller on that absolute value of the sensitivity, and we are going to discuss the control and disturbance behavior. So first of all, let's start with the definition of sensitivity. Sensitivity is the extent to which disturbances in a control system are suppressed. First of all, let's look to an open loop system. This is my plant, this is my system H, and we have a reference signal R supplied to that signal, to that system, and there are disturbances which are added to the output. And now we can say that the output at output signal C is equal to the disturbances D plus HL times R. So the output is a function of the disturbances and a function of the input times the transfer function of my system. So the impact from the disturbance on the output is 1 by 1. So C equals D. So the disturbances are not suppressed but are directly coupled to the output. Now let's look to a feedback system. I have the same process over here, but now I have a controlled system over here. So I have a reference signal and I have disturbances added to the output. And because we can use the superposition rule, we can say that the output is a function of the disturbance and we have the output as a function of the reference signal R. So looking to the reference signal, we can say, well, C is all the system blocks in the forward path divided by 1 plus all the systems in the loop, which is equal to HL divided by 1 plus HL times the reference over here. And when we are looking to the disturbances, we can say the output with respect to the input, which is the disturbance signal over here, is everything in the forward path, but that's only 1. There's no other system block over here, divided by 1 plus every block which is in the loop, which is HL. So this is my expression for the output signal C in my feedback system. So the impact from the disturbance on the output in this situation is 1 over 1 plus HL, because this part is connected to disturbance over here. So we see in this situation, in the feedback situation, my disturbances are suppressed by this function. And the relationship between this function in a closed loop situation and this function in an open loop situation is what we call the sensitivity. So the sensitivity is 1 over 1 plus all the blocks in the loop. 1 divided by 1 plus HL. So HL is the loop transfer function. So when there are more blocks in the loop, then they are all part of HL. And we are mostly interested in the absolute value of the sensitivity, because in that way we know how disturbances are suppressed to my output. So in an ideal case, the absolute value of the absolute value of the sensitivity is 0, or at least is very low. Sensitivity. How can we use the polar plot or the Nyquist plot in order to draw the sensitivity plot or to calculate the sensitivity plot as a function of frequencies? Well, first of all, this is my expression for the absolute value of the sensitivity, which says it's the absolute value of 1 over 1 plus HL, all the blocks in the loop. So now we can also say that 1 over the absolute value of S, so 1 over S is equal to 1 over this function, which is 1 plus HL and the absolute value of it. So we can also say it's the absolute value of HL minus 1. Why do we do that? Suppose this is my Nyquist plot, a fourth order system which has this Nyquist plot. Then this vector length from the point -1 to the Nyquist plot is equal to 1 over the absolute value of the sensitivity. So this is my Nyquist plot. So it changes when the frequencies go up from omega is 0 to omega is infinite. Then we see that the vector length from -1 to that Nyquist plot is equal to 1 over the sensitivity. And why is that? Because it's equal to the vector length from the point -1 plus the vector length from the origin to the Nyquist plot. Because when we add this vector length to the inverse of that vector length, then we have that vector length. So we have to look for deriving the sensitivity Bode plot. We have to look to the vector length from the point -1 to the Nyquist plot and take the inverse of it. So now we can calculate based on this figure how the Bode plot of the sensitivity will look like. First of all, we start off with omega is 0, so that is the start of this Nyquist plot. And we see from the origin it has a vector length of k, but we have to look from the point -1. So in that case, the vector length from the point -1 to the starting point of my Nyquist plot is 1 plus k. So the sensitivity for omega is 0 is 1 divided by 1 plus k, which is this point over here. And when the frequency increases, we see that the vector length from that point -1 to that Nyquist plot will get smaller and smaller, which means that the sensitivity, the absolute value of the sensitivity, will increase. In this point where omega is omega 1, so at that point, we see that the vector length from the point -1 equals 1, because this is a circle with a radius of 1. So in this point, my sensitivity, the absolute value, is 1 divided by 1, which is 1. And that is this point over here. Then when the frequency increases, we see that the vector length from the point -1 will become smaller and smaller, so that my sensitivity, which is the opposite value, increases up to the frequency omega 2, because at omega 2, this is the smallest vector length, and when the frequency keeps on increasing, we see that this vector length also increases, so my sensitivity will become smaller until we get at this point where my frequency is equal to omega 3 and my vector length is 1 again, so my sensitivity is 1 over 1, so it's still 1. And at the end, we end up in the origin, so my sensitivity plot always ends up in 1 over 1, so also in an amplitude of 1. That is what we see. So what does it mean? Well, we want to have a very low sensitivity, because a very low sensitivity means that disturbances are really good suppressed. And that is what we see in the low frequency part of the sensitivity plot, is that the disturbances are really good suppressed because they are much more smaller than 1. The higher k is, and we will see that in the next slides, the lower this value will be. We see also an area in which the sensitivity is higher than 1. And in that case, disturbances are not suppressed, but they are amplified. So you have to make sure that in your system there should not be disturbances present with a frequency within this range, because these disturbances will be amplified because the sensitivity is higher than 1. And that is the negative aspects of sensitivity. You get a good suppression over here, but you get something in return which isn't that good at all. Okay, so now let's have a look what happens when we have a P controller and we start with increasing that KR, so the proportional gain. So in that case, this Nyquist plot will get blown up. It will get something like this. It will be something like this. Another way of looking to the plot is we can also say, well, the point -1, suppose it's here, and the point A, we shift that closer to to the right of the curve, so in the point B. So we scale the complete plot. That's another way of looking to it. But what we see is the following. When this is the original sensitivity plot with the original KR, so with the original proportional gain, we see that when we amplify the proportional gain, we get a higher proportional gain. We start off with a larger vector length through that Nyquist plot. Suppose it was somewhere over here. So we have a better low frequency disturbance suppression over here. But at the contradicting part is that when this Nyquist plot blows up, that there is a point over here, a vector length over here, which is smaller than with the original KR. So in that situation, we get a bigger amplification in this frequency part of my sensitivity curve. So when my P controller is getting a higher proportional value, low frequencies are suppressed better, but in this area we have a bigger amplification of my disturbances. So that is something you should be careful with. Okay, so we get a better noise reduction for these frequencies, and that is often what we want. So we have to make sure by design that there are no disturbances in this area. Now let's look to that control system again. So we have C as the output, R as the input, and D as the disturbances over here, D2, it's called D2. Then this was my sensitivity function. It says it's C over D2, which was 1 over 1 plus HS times AP. And in the ideal situation, it's equal to 0. And C over R is HC times HP divided by 1 plus everything which is in the loop, 1 plus HC times HP. This is what we call the sensitivity, and this is also what we call the complementary sensitivity. And the sensitivity, 0 in the ideal case, plus the complementary sensitivity, when we add these functions together, then it's equal to 1. You can see the numerator and the numerator over here. When we add these, it's the same expression than the denominator of both transfer functions. So it's together, when we add it up, it's together 1. This is the disturbance behavior, sensitivity, and this is the control behavior, the tracking performance, etc. Now let's look to another point, another aspect of sensitivity. Suppose we have made a design with a very good phase margin and a very good gain margin, and suppose we have this as a Nyquist curve, and in that case, well, here's the point minus 1, so this is a radius of 1, so this could be the phase margin, so probably 45 or 50 degrees, which is really good. And in this case, we end up almost in the origin, so the gain margin is really, really, really good. So you could say, well, this is a really robust system. But what happens when you have this kind of a Nyquist plot, that at this frequency, the distance between the Nyquist plot and the point minus 1 will become very small. So the sensitivity, which is 1 over this distance, will be very high. But this is not what we want. This is very close. So this could be when you have tolerances causing a problem. So we want to have a margin on that distance. And just like the gain margin, we often define a gain margin of 2. We also define a sensitivity margin in order to make sure that this distance is not too small. That means that when you look to the Bode plot of the sensitivity curve, we have a requirement on the maximum value of that sensitivity plot, which is often a factor of 2, which is in dBs 20 times the log of 2, which is 6 dB. So we always have to be sure that this amplification over here isn't too high. So again, what we've seen is sensitivity is a expression of how well disturbances, especially in a low frequency area, are suppressed. And when we have a higher proportional value, we have seen that the suppression for low frequencies is even better, but we get a higher amplification in this area. So we have to make sure of that there is no noise in that area because the disturbances are amplified over here. So that is not what we want. So that is all caused by what we call the Bode sensitivity integral. The Bode sensitivity integral is this expression for a system which has at least two more poles than zero. And it says that when you suppress the disturbances even more, so when you have a higher amplification over here, this will be suppressed, but you get an amplification over here. And the more you suppress disturbances over here, the more you get an amplification over here. So you have a so-called water bed effect. And again, you have to make sure that there won't be any disturbances present in that area because they will be amplified, and that is of course not very useful for your system. So let's end up this presentation with an example in which we want to create a sensitivity Bode plot based on a Nyquist plot. So for instance, this is my Nyquist plot for a fourth order system, and we want to draw the sensitivity plot, or we want to look into the absolute value of the sensitivity as function of frequency, like the Bode amplitude plot. So first of all, we start off with the vector length from the point -1 to the Nyquist plot over here. And this is my start value, my start frequency, omega 0. And we see that this has a length of almost, well, 1.4. So the vector length of -1 to that point over here of the starting point of the Nyquist plot is 2.4. So my sensitivity at this frequency, omega is 0, is 1 divided by 2.4. So it's almost 0.4. Then my frequency increases and increases and increases and increases, and we see that the vector length from -1 to the Nyquist plot decreases. So that means that the sensitivity will increase. And here we get to the point omega 1. So my frequency at omega 1, we see, because we have drawn a circle over here with a radius of 1, that this vector length is equal to 1. So my sensitivity is 1 over 1, which is 1. Then my frequency keeps on increasing, and at this value, well, we see that this is a circle with an amplitude of somewhat more than 0.7. So this vector has a vector length of somewhat more than 0.7. So the sensitivity at omega 2 is 1 over 0.7, which is something between 1.4 and 1.5. That is the closest point from my Nyquist plot towards the point -1. So this is the peak in my sensitivity curve. And when the omega increases, we see that the vector length also increases over here. And at omega 3, we see that the vector length is 1 again. So also my sensitivity is 1 over 1, which is 1. And here at the point omega 4, we see that, well, the vector length is somewhat more than 1, let's say 1.05, and then my sensitivity is 1 over 1.05, which is somewhat higher probably than 0.9. And we end up with the Nyquist plot in the origin, so also the sensitivity curve will end up in 1 over 1, which is 1. So then this is my sensitivity plot. We've seen at omega 0, my amplitude was 1 over 2.4, which is 0.4. Then my frequency increases over here, and at omega 1, we saw that the vector length was 1, so my sensitivity is 1. And then my frequency increases up to omega 2, and at omega 2, my vector length was almost 0.7. So we have seen that that the sensitivity is 1 over 0.7, which is somewhat more than 1.4, and then my sensitivity decreases because my vector length from point -1 increased, and at omega 0, we saw that the vector length was 1, so also sensitivity is 1, and then we end up here at 1. One last remark. This is an absolute magnitude for my sensitivity. Very often sensitivity is also defined in dB. So in that case, we have to take the 20 log of that sensitivity value. So the sensitivity then always ends up at 0 dBs. Well, that was all about sensitivity. Thank you for watching, and I see you next time.